Hey, how's it going today? So here I am back again. I'm going to show you how to do the mixing water of different temperatures problem. Okay, so let me share the tablet screen and we'll go from scratch right here. So I'm looking at the problem statement that I'm presented with, and it says I've got a container with 50 grams of water, and I'm going to call this container one. And that means that mass one is 50 grams of water. So there's our water. And we're going to mix that with a second container, container two, that also has 50 grams of water. And since they're water, they both have the same specific heat capacity of 1 calorie per gram in degree C. 1 C is equal to, let me get rid of that, 1 calorie per gram degree C. And the initial temperature of this, the water in the container one, T1 initial, T1I, is 20 degrees C. Now, in the problem that I'm given, the temperature of the water in container two, or T2I, is equal to 63 degrees C. All right, so we're going to take the water from one and pour it in the bigger container, and take the water from two and pour it into the bigger container. So you might guess that the final temperature, TF, is going to be somewhere in between 20 and 63. Now, using your intuition and knowing that the masses are the same and they're both the same material, water, then you could assume it's going to end up halfway in between. And that is indeed what happens. But let's do all the math and I'll show you how it works. So the heat transferred into the water of the first container is going to be positive because its temperature is going up. Q is equal to mc delta T, and I'll call that M1 there. And that's going to be equal to the amount of heat lost, or negative Q, for container number two. That'll be M2 C delta T. Now remember, delta T is always final minus initial, TF minus TI. So this does take a little bit of algebra work. Let's put these together and see what we get. So I know that this expression is going to be equal to this expression over here. Actually, that should be a minus sign in front of the M2 because there's a minus sign here. Okay, now let's expand delta T on both sides. So on the left, we have M1 C TF minus T1I. And that is going to be equal to minus M2 C TF. That's an F there, not a, those TF, let me make it clear, minus T2 initial. Okay, well, that's progress. Let's think about what we're trying to find, and we want to isolate TF in this relationship here. So to do that, I'll need to distribute the M's and C's through those parentheses and regroup things. So I've got M1C TF minus M1C T1I. That's a C there. And that's going to be equal to minus M2C TF. And we've got a minus sign here and a minus sign here. So that makes it a plus M2 C T2I. Okay, so what's our next step? We need to get TF together on one side of the relationship, this equation here. So I've got TF in this expression, and I've got TF in this expression. So what I'll do is I'll add this to both sides. And when I add M2C, pardon me, put the parentheses there. When I add M2C TF to both sides, it's going to go away on the right. And on the left, I'll have M1 C TF plus M2 C TF. All right. Now, similarly, I want to get everything that's not TF away from the left side. So I'm going to take this, and I'm going to add this to both sides. I'll just do that now. So what am I left with on the right side after I added M2C TF to both sides? Well, I have M2C T2 initial. And I'm going to add the thing circled on the left, M1 C T1 I, T1 initial. Okay, I need a little more space here. Whoops, not too far. I'm still getting accustomed to this thing. All right, so look at the left. We can combine these and say that this is TF multiplied by M1C plus M2C. And on the right, I'm just going to leave it the way it is because we've got M1s and M2s. And even if you had different liquids, say, for example, water and alcohol, you could also put a subscript on the specific heat capacity and keep track of those as you go through this process. Okay, so on the right, we've still got M2C T2I plus M1C T1I. But we got TF all by itself on the left, and that's a good thing because now I can divide both sides by this thing in parentheses. And when I do that, I get M1C plus M2C. And this one goes away because I've done the same thing here, M1C plus M2C. So those cancel each other out. And I end up with an expression for the final temperature in terms of everything else that we already know. TF is equal to this expression. It's a little bit long, but if we've done the algebra right, we can put all the numbers in now. M2 and M1 are both 50 grams. The specific heat capacity is 1 calorie per gram degrees C. And that's going to be plus M1, 50 grams. Oh, forgive me. I forgot the temperature there. What is T2I? Well, in my case, that was 63 degrees C. I'm going to add that to M1, which was 50 grams. And C for water, again, is 1 calorie per gram degrees C. I'll put a parentheses around that. I guess I forgot it there too. And T1I was 20 degrees C. Now I'm going to divide that whole thing by M1, 50 grams, multiplied by 1 calorie per gram degrees C. And M2 is 50 grams, multiplied by 1 calorie per gram degrees C. And the reason I've carried all that through to this point is because I want to look at the units. And when we're done, the units should be degrees C. Okay, so let's do the math here. And when you put this in your calculator, I think you can just do it the way it is because I can do the bottom of this fraction in my head. I would say 50 multiplied by 1 multiplied by 63 plus 50 multiplied by 1 multiplied by 20 equals, and then take that answer, which is 4150. I'll leave the units off for the moment. And that's 4150 divided by, and then I can do the bottom independently, or I can use the parentheses buttons on the calculator. So if I just hit equals there and I get 4150, then I would say divided by, open parentheses. I need to put the whole expression in parentheses for it to work out right. 50 times 1 plus 50 times 1, well, that's going to be 100. So if all the units work out, which we'll look at in a minute, I end up with a final temperature of 41.5 degrees C. And you can see that that's about halfway between 63 degrees C and 20 degrees C. Exactly halfway. All right, so that's how you work the problem. Let's look at the units. And I think I'll just use what I've got written there instead of rewriting it all. Grams cancel out there, and degrees C cancel out there. Grams cancel out, oops, I didn't mean to erase that. Grams cancel out there, and degrees C cancel out there. So what I've got on top is calories for the units. And what do I have on the bottom? Well, grams cancel out here, and that leaves me, grams cancel out here. So the units for the number on the bottom are calories per degree C. Okay, so it's not obvious, but the final unit here is calories divided by calories divided by degrees C, but that's in parentheses. So what that really means is you can take that fraction on the bottom, pull it out, and flip it over. So we've got calories multiplied by calories with degrees C here. And the calories cancel each other out, and indeed I end up with a final unit on the answer of degrees C. So that's it. That's how you do that kind of problem. For our class, that's a little bit advanced, and I probably won't ask it again because we didn't really cover any practice problems like that. But there you go. As promised, solution to mixing two fluids. Again, you can put subscripts on the specific heats and do it for two different fluids. And you can do it for two different masses. The way I work this, if you have an M1 that's 100 grams and an M2 that's 50, that carries right on through. And you can do it for that as well. Okay, that's it for now.